So let's move to the next talk, the final talk of this day. Let's see. Hey, by Paris Smaragdis. Paris did his graduate studies and postdoc at MIT, then worked in various labs, including Merle, and then Adobe Research, and since he doesn't say, since when are you at UIUC? When did you join UIUC? 2011, 2010? He's now at University of Illinois Urbana-Champaign. He's going to talk today about NMF and deep networks, so very much in the theme of the day. Right. Wait a sec. I need to launch a new recording. Hold it.
We have sound. Okay. So thanks for the introduction. Thanks for having me. Whoops. That's my sound check. So today I'm going to talk about, or rather ramble about a whole bunch of things. I decided not to play any fancy demos or blow your mind in any other way. But I wanted to talk about some of the directions that I'm seeing people moving towards and how they relate to some of the work that's done before and the sort of interesting connections that, that I've seen. So I'm mostly going to talk about going a little bit back to the basics about how we do processing of sound. We've all taken some DSP courses. We all have some inherent biases. And one of the things that I don't like is to sort of blindly use a lot of these tools that I've been taught I should use and then not really question them. So in the process of doing that, I'd like to rethink a little bit about how we do a lot of NMF processing and also a little bit about how the neural nets come in. So the personal motivation is that I really hate making assumptions whenever I design something. I really like to purge as much of the DSP tradition as I've accumulated over time. And the excuse for that is that I never actually took the DSP course at MIT, but I took the machine learning course. So it's my duty now to kill DSP. But one thing that I don't like is, of course, you take a DSP course, somebody tells you, hey, the Fourier transform is a great tool. OK, it's a great tool. I'm going to use it for the rest of my life. And we don't really know why we do that. So and what I really want to do is throw away that information and then start thinking a little bit more about how we can evolve an intelligent listener. My main research interest is making machines that understand sound. And part of doing that is trying to follow kind of an evolutionary perspective, right? We used to be single-cell organisms a few billion years ago. And after listening to sounds for all this time, we've finally grew ears. How can I make software that does the same thing? I don't want to teach it how to sound. I want to let it learn by itself. So these are the things that, that we're going to be going up against. So I'm going to start with a very simple case study. It's an example that many of you know. But it's a good way of sort of stepping through this process and kind of showing you what I mean. So let's say we want to analyze something like a simple piano recording. Okay? When I was a grad student, the standard approach was that you have to assume that you have some music structure. So we have notes, we have scales, we have chords, all that stuff takes a while. We have to assume that you have a piano. There's a transient, there's sustain, there's harmonic. The tuning goes off as you go in the high notes. All sorts of information like that. You have to assume that you have polyphony. A lot of those piano notes will happen at the same time. And eventually, you make this really, really big, complicated model. Somebody gives you a piano recording, and you try to fit the recording to that model. And there are two things that I've seen happen. One of it is that you really forgot something forgot something to put in the model, so it didn't work that well. Or the model is really great, but there's no way to actually fit your data to it because it's insanely complicated. And I'm sure a lot of us here have been sort of in this position. The approach that I like a little better is to basically assume nothing and just say, well, there's data coming in. The data has some inherent structure into it. Let me just find the structure from the data. I don't need to know about Western music and piano tuning and acoustics and all those things. That information is actually captured inside the signal. Let's try to find this. So let's start with a very simple example. So here's a spectrogram of the sound we're going to be hearing and seeing over and over. And it's just basically 3 notes. Each note is played in isolation at the sort of first half of the recording, and then at the second half, all 3 notes are played with a little bit of overlapping. So here's what it sounds like. So we're going to use that as a sort of the starting point. So about 15 years ago or so, we started doing a lot of work with non-negative modeling. And the sort of one of the approaches that came out that kind of encapsulated the ideas that I've been describing so far was basically to say, let's take the spectrogram, let's factorize it, find some low rank structure, and maybe something useful will pop out. And it was a fairly simple sort of concept. There were a couple of key issues. So simple way that you would do an NMF model would be to say that, let's see, do we have a mouse? We're going to take the magnitude spectrogram. We're going to approximate it as a product of 2 matrices. And then all of those matrices have to be non-negative. And ideally, what you'd like to see is that you're going to start with your data being as a spectrogram. And then we're going to get a bunch of columns on the W matrix. These are going to correspond to something like a harmonic base of sorts or vertical structure. Then you're going to get a set of rows on your H matrix, and these are going to be the activations of those bases, right? So it's a simple sort of low-rank decomposition. And what was very nice about doing something simple like that, it's like 10 lines of MATLAB code, is that after you actually give it an example like the one I've shown, you end up with these outputs. So on the left, you get the 3 columns of the W matrix, which look like what? Right, the spectra of the nodes. And then on the right, you get the activation of those spectra over time. So what we're seeing in that representation is that this particular spectrum, or sort of a spectral entity, gets activated at the beginning, and it's sort of loud, and then it sort of slowly dies down, a couple of blips over here, and then it gets activated in the end again. Second component, again, we see another harmonic series. This is when it's activated, then the third one. So clearly what happens is that this component has found the first node, this component has found the third node, and this one has found the second node. And it tells us how those are activated over time. Now, the reason why I was very excited when I first stumbled on that was that I didn't teach my system anything about music or sound, right? Here's a spectrogram, and then poof, music comes out. And that was pretty exciting. And then the other sort of part that made it even more interesting is that I could basically recompose my data by using only a subset of those components. So now I could take this very simple decomposition, and I would say, if I were to take the ith column of W, multiply it with the ith row of H, that's basically going to give me only 1 dimension of my data. And then I could take that magnitude spectrogram, effectively modulated by the phase of the original input, and then hear what that sounds like. And if you do this, you basically get these 3 sounds that I have over here. Let me play them. So here's the first one. So it's kind of stumbling on one of the notes. And here's the second one. And here's the third one. So in some way, we're finding structure, and we're able to extract some of it, not perfectly yet. So I think I presented that 2013 at WASPA, which was last week again. That's where most of us came from. And since then, I've been getting a lot of flack for it. So here are some of the things I've been hearing about. Why are you using the mixture phase? This makes absolutely no sense. Surely there are better phase values you could be using, which is a fair argument, right? Another one is, why are you not using the mixture phase? Surely there's a lot of information in the complex number. You're taking the magnitude of the spectrogram. You're doing some processing. Why are you throwing away so much information? You should be doing some kind of a complex decomposition, which, again, is another fair argument. People who are much more into math, they're going to say, well, the modulus of the short-term Fourier transform is not additive, right? You take 2 sounds. If you add them together, the STFT of their sum is not going to be the sum of their STFTs, which, again, is a correct argument. So everybody was convinced that the model is wrong. I don't care. It didn't change anything. What I really cared about is not so much sort of technical details of that sort. There are other issues. Why am I using complex valued discrete Fourier transform? I have a real waveform, and then I took the DSP course. Somebody told me you have to take DFTs, and OK, I did that, and here's the spectrogram. Why bother with complex numbers, phases, and all that business? I didn't like that. Why am I using a spectrogram? I've been taking spectrograms since forever because that's what I've been told to do. But I instinctively always use a Hopf size of 1024. My Hopf size is always going to be 25%. Always use a hand window. These are things that I do instinctively, but I never really question them, right? And I'm assuming most of you here do something of that sort, right? So these are great tools. I'm not necessarily convinced that they're the optimal tools to do a lot of this work. So what I wanted to figure out is a way of justifying them and seeing if I could replace them with something different. So let's try doing that. So the first goal is to avoid complex numbers. Never liked them, still don't, and I'm happy to say that I got rid of them now. So in order to do that, we're going to do a little bit of rewriting of what we have. So we're going to take our time waveform. We're going to cut it up into small pieces of sort of L samples at a time. And that's going to be sort of a frame representation of our waveform. And we can decide on whatever hop size or size of a window that we like. And then if I wanted to represent the short-time Fourier transform as kind of a linear algebra operation, what I would do is I would take that matrix that has all my time frames. I would multiply it with some diagonal matrix that would maybe include a window, hand window, whatever. And then I would multiply that with the Fourier matrix. Okay? So that would take the windowed Fourier transform of every chunk of my sound. And that would result in a matrix that would have that Fourier transform in all of its columns. Okay? That's how you write a short-time Fourier transform if you like MATLAB. So, OK, so that's nice. So what we're going to do now is say that we don't want to use the discrete Fourier transform. So we're going to use a discrete cosine transform, which is a real valued matrix. We don't have to use these complex numbers. And it keeps me a little happier. And in this particular case, this is what all these quantities look like. So top left, that trippy-looking matrix is the DCT matrix. You can see that it's got a sinusoid, or a sine and a cosine in every row. On the top right, we have the sort of what I call the short-time input matrix. So it's basically all the frames from my time waveform stacked next to each other. If I were to multiply these two together and see what comes out, we're going to get the matrix on the bottom. Right? This is the transform, the magnitude of the result of that product in the bottom, right? And it looks somewhat familiar, like it sort of kind of looks like a short-time Fourier transform. It does have a couple of issues. So here's sort of a zooming in into just a sort of small portion of that sound. And what I'm doing is comparing my short-time Fourier transform versus what I'm going to call the short-time cosine transform because it's not quite an MDCT. And what we see is that for the short-time Fourier transform, whenever you have a lot of energy in one of the frequencies, you have a strong peak. There's a little bit of crosstalk between the frequency channels. So the neighboring bins also get a little bit of energy. But it's fairly easy to sort of interpret. If we go to the cosine transform, we see a slightly different behavior, right? We're seeing that we have this interesting pattern in our coefficients, and we see we have all these holes. Now, what's going on here? Every frequency that we have with the Fourier transform is basically represented by a complex component, right? There's going to be a real cosine and an imaginary sine, okay? And what we do is that we mix those two functions together, and if we modulate the levels the right way, we can approximate a sinusoid of every phase that we want, okay? So it's basically a smart way of combining a sine and a cosine and trying to shift their phase arbitrarily. So how much energy the output is going to have is going to be basically the sum of the squares of those two components, same frequency components. The exact phase of the output is going to relate to the relative amplitude of these two components. So that's what the short-time Fourier transform does. So in this case, we're plotting about 15 frequency bins in the top plot, so we get basically 15 complex series coming out of it. On the bottom part, we have the equivalent frequency range using the cosine transform. We're not going to have a complex part in this case. It's all going to be real valued. And now, instead of having a real cosine and imaginary sine, what we're going to have is a real cosine and a real sine, which are going to be assigned to different bases or different coefficients. So now we're going to have to plot 30 coefficients as opposed to 15, because we're going to have twice as many bases to cover the frequencies. And what you're seeing is that we have this interplay between neighboring frequencies, right? So for example, over at this point, you see that when one of the bins is very loud, the other one is not. And then they sort of flip after a while, and they flip again, and they flip again, right? So that's because there's always going to be sort of a little bit of a mismatch with the exact frequencies. And if you're trying to approximate a new phase, or you have a little bit of jitter, you basically have to fade in that sine and cosine of the same frequency and alternate them in such a way that you recreate the components that you want. And that makes a DCT very annoying because it doesn't have this nice smooth structure that you get from the short-time Fourier transform, which is probably why we don't use the DCT as much. So that's a little bit of a problem, because now if I wanted to do anything like any of those NMF tricks, it wouldn't really work that well, because I would have twice as many components corresponding to every frequency, and it would completely mess up all the co-occurrences and things of that sort. So for now, what we're going to do is do something really, really simple. And we're going to say, well, we don't really like the fact that these things sort of jump in and out. So what's the easiest way of getting rid of that behavior? We just smooth it out, right? So here's what happens when you do that. I'm going to take every row of my cosine transform, and I'm going to sort of low-pass filter it, or it doesn't matter what we do, because we're going to throw that out in a minute. But basically, it's going to start looking a little bit more convenient for what we want to do, okay? So now, qualitatively, what we have in the top plot is similar to what we have in the bottom plot. So now, what do? Well, we're going to take our input. We're going to take this sliding DCT transformation. We are going to take the magnitude of that. We're going to smooth every row of that representation to get rid of all the jitter that we had. And we're going to call that our smooth magnitudes. So now, these are going to be functions that tell me how frequencies get modulated over time, which is exactly what the short-time Fourier transform modulus is, right? Since we can treat it as such, it's going to be a non-negative sort of entity, so we're going to factorize it. So we're going to take those smooth magnitudes. We're going to say these are going to be equal to some low-rank non-negative factorization. And we're basically going to be doing exactly what I've done before. And the only difference now is that we're not going to have a phase that we started with that we had before, right? There's no phase in this transformation. So now if we want to go back in the time domain, we have to do something a little different, even though it's kind of the same thing. We're going to take the reconstruction of a spectrogram of every component individually. And that's going to be sort of a modulation mask, if you like. And then we're going to take our original input coming out of the cosine transform, and we're going to divide that by the smooth magnitudes initially. Okay? Now imagine for a moment that our approximation with the lower rank transformation was perfect, and we're trying to reconstruct everything. What eventually would happen at this point is that the W times H would be exactly equal to M, and these two terms would cancel, and we get perfect reconstruction, which is what we want. Now we're going to say that we only care about one component. So what we're doing is that we're demodulating all of the frequencies by their activation over time. And then we do another sort of a modulation where we only modulate the parts that we want, and everything else stays close to 0. Okay? So we're just substituting the envelopes of every frequency track over time. What that is going to give me is the coefficients of only one component, or the contribution of only one component. Again, that's going to be a matrix that's going to have one of those contributions per time step. I multiply that with the inverse discrete cosine transform, and then I get my approximation of a time frequency waveform. Okay? You can also think of the same thing as the exact equation works again with something like the discrete Fourier transform. What we do with a discrete Fourier transform is that we don't really have this smoothing filter. This operation essentially extracts the phase component that we care about, and we just remodulate it by whatever the components reconstruct. Okay? So it's not very different, but it's a different way of thinking it. And qualitatively, it basically produces the same results. I'm not going to show anything. It's almost exactly the same as the short-time Fourier transform. OK, so that's nice, because it tells me that I don't have to use complex numbers anymore. That makes me a little bit happy. But NMF has been around for 15 years or so, so we have to keep up with the times, right? So there's not a lot of stuff you can do to extend NMF. As far as linear algebra goes, it's a complete oddity. It doesn't fit anywhere in any textbook you're going to find. It's not very straightforward to extend and generalize. If you wanted to make an NMF that had some kind of a temporal structure, it's a huge pain in the ass. It's a lot of math that you have to figure out. You have to be very careful, and it really takes forever. And of course, nowadays when I get all the students coming to me, everybody wants to do deep learning or neural networks. So okay, at some point I said, okay, let's do that. Let's see how we could take what we have and try to reimagine it as a neural network and see what difference it makes and see what the advantages are. Ahead of time, of course, I knew that neural nets are very easy to reconfigure. It's very straightforward to extend them and sort of add new bells and whistles, which are very difficult in the NMF world. And there's a very rich ecosystem from which we could get ideas. So how do we do that? So very simple idea. What we're going to do now is just forget about the front end and just look at the NMF core and just make a couple of observations and a little bit of rewriting. So what does NMF do? It says that we're going to take a non-negative input, and we're going to break it into a product of two non-negative matrices. That is not a very useful way of defining the problem that we're trying to solve. So what I'm going to do is sort of shift things a little bit around. And I'm going to say that the activations that this low-rank transformation is giving me are going to be equal to some kind of a matrix, which is some kind of a pseudo-inverse of W that only produces positive numbers, which linear algebra books will never tell you how to find. And you have to multiply that with your input. And what I've done now is I've created a formulation of the NMF equations, which is basically a feed-forward version, right? An input comes in. It gets multiplied with something. It produces my low-rank decomposition, right? So same equation, but different way of thinking about it. Now, taking those equations, if you stare at them long enough, if you read enough about deep learning, you can say, well, I could probably put these two things together and make an autoencoder. So what we're going to do is we're going to take our input, goes to a first layer of a neural network. The first layer is essentially going to represent this W star matrix. That's going to project our data into a non-negative subspace. And the way that we guarantee that things get projected to a non-negative subspace is that we're going to have an activation function which produces only non-negative numbers, or at least positive numbers. I could have a rectified linear. I could have a soft plus. I could even take absolute values. Doesn't matter. They all work pretty much the same. So now I found this feed-forward transform that's going to take me to a low-dimensional non-negative space. That's pretty cool. And now what I have to do is find a way of ensuring that this low-dimensional representation is a good explains the input well enough. So we have to have the second half of the autoencoder, which means that we're going to take that low-dimensional representation, multiply it with a W matrix, or the equivalent of a W matrix, and that should recreate my data. So that becomes a very simple network. Basically, input and output are the same, and you're trying to find a non-negative low-rank decomposition that gives you what you want. Both layers have to have an activation that produces non-negative or at least positive outputs. And if you do that, it's actually a very simple thing to implement. It's just a few lines of code in any standard neural net toolbox. And what's nice about it is that now we know exactly what these two layers are doing. Most people complain all the time neural networks are not that great because they're black boxes and all that. We know exactly what our two layers are doing at this point. So what does that do? So here's the output that we got from doing this thing on the initial data applied on the discrete cosine transform. And what we're seeing is that qualitatively it's pretty much the same thing. The only thing that's a little different is that you might see a little bit of a slope at these onsets because we're doing this smoothing operation that I mentioned before. Is that a deal breaker? Not much. If you try to see what the learned components look like, it's a little bit more interesting. We see that they're a little better than before. There's less crosstalk between the components. And another thing that we see is that it's very easy for this network to give us sections that basically have absolutely no energy for a while. And the reason why they do that, in this particular case, I was using the rectified linear unit activations. It means that whenever my W star matrix gets any value which is below 0, it's going to produce an output that's a 0, right? That's what the other values do. Which means that it's very easy to output a series of zeros, whereas with NMF, it's something that's very difficult because it's really a boundary condition that everything has to align properly to get. It's very easy to get very big magnitude negative coefficients that basically enforce this 0 behavior. So what do the components sound like? Again, here's one of them. Second one. And I'm using too few frequencies. That's why you get some bleeding between the chords. Don't worry about that yet. But the big thing that we gained right now is that we're really getting some silence. So here's a comparison of the NMF components using a DFT front end, and the same thing using and the neural net components using a DCT front end. And what you'll notice is that there's a lot of stuff going on here that you see and you can hear in the time domain, and those things are completely obliterated when you use this transformation. So, so that's kind of one simple way to start doing NMF using neural networks. And the reason why this is a good idea, if at all, is that it allows us to do a lot of extensions. So now it's going to be trivial for me to say, well, how about I make my middle layer being recurrent? It's just, I just switch a couple of functions in my code, and it's very easy to do. I don't know what it means, but it's probably going to do something interesting. Can I make a hierarchical NMF model? Of course. I could have my input coming in. I'm going to have my first low-rank decomposition that takes me into, say, 2 dimensions. And then on top of that, I'm going to have a rank 1 decomposition. And then I can blow this up again to my input. It becomes a much deeper autoencoder. And now what I'm going to get in these subspaces is probably different ways of expressing my data in different dimensions. Maybe I could have nodes, intervals, and chords, or something of that sort. So it opens up a lot of interesting possibilities, so we can play around with it. So, so at this point, I've addressed sort of some of my, my concerns, but I didn't really go far back enough to address one of the things that still bugs me, which is why are we using the DCT? My initial comment was that, well, I don't want to use a DFT, so let's just change one letter. It should be fine, right? But it's still being lazy. What's so special about sinusoids? Why do we have to use the sinusoidal basis to describe sound? And if you sort of dig enough into the literature to figure out why the DFT and the DCT are useful tools, we actually get some interesting insight. So, so if you wanted to explain, for example, a discrete cosine transform, the way that it works is that if you were to take a Markov process as a signal and then sort of stack it up into a matrix the way that we did with frames previously and get this T matrix that we had before, if you were to take the covariance of that, it's going to be a Toeplitz matrix, right? It's basically going to look like this. It's going to say that the further away you are from a frame, the less correlated you're going to be. What it tells us is that neighboring samples or neighboring frames are similar, distant frames are not so much. If you have a structure of that sort, it turns out that sinusoids are the eigenvectors of that particular structure of a matrix. And the reason why we use the DCT and the DFT in the case of sort of circular matrices is because they're the best way to diagonalize the covariance matrix of these types of Markov processes, which is great. The only problem is that that happens in some limit of all sorts of certain assumptions. If my data is only comprised out of 3 nodes, I only use a subset of all the frequencies. So why would I want to use such a big sort of transformation space when I could actually do much better with fewer dimensions? So now, instead of trying to do something like the discrete cosine transform, it's very easy for me to say, I'm going to do something like PCA. I'm going to get a transformation which is going to be optimal for my data and just for that data. And then I'm going to use that. So no reason to use sinusoids and things of that sort. So how do we do this? We're going to take our the matrix that has the frames that I mentioned before. We take its covariance, take its do an eigen decomposition, and that's going to give us our feature transformation matrix. That's what we're going to replace our DCT with. And if you look at it, it looks quite interesting. These are going to be the eigenvalues, where they essentially tell us that more than 35 or so dimensions, you don't really need to keep any more coefficients around. You don't really get that much gain. The eigenvectors themselves look like the functions that I'm plotting in the bottom. And of course, you notice that I didn't quite escape the sinusoids yet. But at least it's only using sinusoids which are relevant. In fact, what you'll see is 3 pairs of sinusoids which are off by off in their phase, and it's going to use that to basically reconstruct different phases. And then we get a whole bunch of components which are used for transits and sort of noise and things of that sort. So that's a little bit more satisfying to me, because now I didn't have to say sinusoids are good. Sinusoids were shown to be good, or at least these types of sinusoids-ish have been shown to be good. So that's nice. So what do we do now? Well, we're going to do the same thing again. We're going to do a projection. Oh, and one thing that I didn't mention is that on the top right, you basically see how our data gets projected if you do this PCA transformation. So what we see is that the first 2 coefficients basically correspond to the first node. You can see there's positive and negative activations because we're not doing the absolute value. A few more components up here correspond to the second node, third node, and then can kind of see them getting mixed later on. Okay. So what happens if we take the output of that, put this into our neural network NMF framework? We get this output, which absolutely sucks. The excuse for that is, well, we started with 128 dimensions. Now we're down to 40 dimensions. Of course, things are not going to be that good. But we're seeing things that we don't like. There's absolutely no harmonic structure in the components that we get here. And we also see that we get a lot of crosstalk between the activation of our components. So it's not quite doing the right thing. It's confusing things. And if you think about it, it's something that's sort of a little bit sensible. And then the question here becomes, well, why would you want to use PCA? And of course, the answer to that is for the same reason I use the DFT, because that's what I've been taught. We don't really care about orthogonality in this case. Doesn't mean anything as far as our hearing system goes. Maybe we should be using something else. We could use something like ICA, which we know produces much better bases than PCA. Maybe there are other methods. It's not clear what the optimality criteria are. So I'm going to be lazy and sort of go with the neural network way and say, well, we're just going to make an autoencoder, and it's going to tell us what the best bases are for our data, and we're going to use that. And for now, it's kind of an arbitrary decision. It's going to sort of make sense in a minute. So what does that do? So we're going to do a very simple setup. We're going to take our input data. We're going to have one matrix or one layer that transforms that data to some subspace or some other space. And then we're going to have another matrix, which is effectively going to invert that transformation. And all of those things basically should give us the input as an output. So we're going to try to figure out a W1 and a W2 that, when given T as an input, provides T as an output, which sounds like a very silly thing to say, because right now there's infinite solutions, and it's kind of a nonsensical equation. So we're going to make sure that this is going to be a low-rank transformation, so we don't keep all of the dimensions. And then it's still not going to be very well defined. So we're going to add a sparsity penalty, where we're going to say that whatever space you project our data in after the first layer, I don't really want to see a lot of energy. I just want to see a few coefficients being active, because effectively that's a nice way of describing what's going on. So we can take the piano example. We do that. The bases that we get are shown on the top over here. They're still a little bit sinusoidal, but thankfully not as much. And then if you look at the magnitudes that we get on the bottom plot, they actually make a lot of sense. We see, for example, when the first node is active, this component or this coefficient ends up having a lot of energy. It gets complemented by this one and maybe a couple of these. When you have the second node, then you get this coefficient and that one, and these two maybe. Third node gets a completely different pattern, and then you can kind of see all of those things come in when all of the three overlapping nodes come. So that's kind of neat, because now we have an equivalent of our short-time Fourier transform, but it's completely sort of optimized for the data that we have. And if you sort of listen to what that sounds like, this is the reconstruction for the full set. Maybe. So very low quality, because in this case, I'm only using something like 30 components or so. We can fix that in a minute. So what happens if we try to do the neural net NMF on this? Well, now it's going to look a little better if the slide changes. Hello? Yes? No? There we go. So now we notice that the results are going to be super, super clean. You see that those little blips that we had in the previous examples, they're mostly gone. There's a very tiny bit of it on just one component. It totally gets superposition. It doesn't get things mixed together. When there's silence, there's complete silence. You can see that in the waveform, that you would never get NMF to give you things which are silent as that. And it does pretty much a perfect job in sort of segmenting and sort of understanding what's going on. So that's a little, that's nice. But of course, there's nothing that much more that I couldn't have done before. So now let's see what else we can do to make it a bit more interesting. So probably the first thing you're thinking right now is that I'm being very shallow. Why do you need to have two steps? You have a front-end transform, and then that's fixed. And then you try to do a subspace transformation. If you were a true deep learner, what you should do is actually stack everything together, and hopefully it's going to give you the right answer. We would like to have a deep network where the first layer is basically going to try to do something equivalent to a DFT or a DCT or some kind of a front end. The second layer should basically do what NMF should be doing, and then you're going to have the mirror part of that to make a deep autoencoder. So how do we do that? We're going to have these sort of ugly equations. There's a pretty picture after that, so you can doze off for now if you don't care. So analysis step, we get our T matrix coming in that has all the frames in the columns. Gets multiplied by a matrix. That's going to be our feature transformation. We get a whole bunch of coefficients. We take those coefficients, take their magnitude, and we convolve them with a smoothing function, what we did with the DCT. And that's going to give us the smooth envelopes. We take the smooth envelopes, we put them into the second layer. We're going to have our NMF-like decomposition. That's going to take us to a non-negative subspace. Once we get there, we need to have the second part of the autoencoder. So we take the non-negative subspace, linearly transformed, sort of a positive activation function. That's going to give us the reconstruction of the smooth amplitudes. And then we do the trick that I've shown before, where we basically demodulate the coefficients with the true envelopes and then remodulate it with our approximation. That's going to give us the approximation of the coefficients. And then final layer, we basically have a linear transform that should take these coefficients back to the time domain. Okay? So it's a sort of a fairly deep autoencoder. Of course, this is going to have an infinite number of solutions. So what we want to do is regularize it in some way. So what we're going to say is that we want to make sure that the input and the output are as similar as possible. And it's OK to use something like mean squared error. And then we also want to minimize the L1 norm of the coefficients. We don't want the coefficients to be too active. We only want to keep some of them. And for good measure, we could also minimize the L1 norm of the non-negative subspace. We don't want to have activations that happen all the time together. We just want to make sure that they're as separate as possible. What does that look like if you're more into pictures? Well, again, fairly straightforward. Your input is going to be a time series. We're going to cut it up into small pieces. You're going to make this matrix that has all these frames. If you multiply that with our transformation, it's probably going to go into some lower subspace, which is going to be just the frequencies we care about. So basically, we get the same number of frames, but lower dimensions. Then we have this rectify and smooth step over here. So we get the sort of the smooth envelopes. And then the blue section is effectively NMF, right? Inputs come in. First layer projects to low dimensional non-negative space. Second layer takes you back to do the reconstruction. And then in parallel, what you're doing is that you're demodulating the input with the smooth coefficients, smooth activations. And then you remodulate it with whatever comes out of NMF. Put all of those things together. That's going to be your approximation of your coefficients. Inverse transform. You get back the frames. You do overlap and add. And then you get your time waveform in the end. OK? So what does that do? Again, using the same example as before, it actually gives us something that's very sensible. So let's see. These are this is the transformation, the front-end transformation that happens. So again, it finds the periodic sort of nature of our data. And now what we're seeing this time is that they don't really look like sinusoids. They look more like little piano waveforms, which makes me very happy because that's what the data was, right? I was expecting to see that. If we look at the output of that transformation, this is what it looks like. Again, we see that every node ends up having a different pattern of activations over time. So it's kind of like you can think of it as a kind of a smart way of a smart spectrogram of sorts. If we rectify and smooth, this is what we get out of it. This is the reconstruction after we go through the non-negative network. And then just for comparison, this is what the input looked like. This is what the approximation looks like. And then most importantly, these are what the hidden activations look like. Now, they're not going to be as good as before because it's a small sort of toy example. The parameters are way too many. So it's kind of an overkill analyzing that way. But the whole point is that I've learned a whole bunch of things about my data, which it was sort of embedded in the data. I didn't have to say, well, we have sounds, they're periodic, there's notes, and things of that sort. All of the structure came out. The only thing I had to say is that I have a series of stages that are somehow connected. The reason why the results are not that good as before is, of course, we're operating in this case in 12-dimensional space as opposed to 128, which is what we had before. If we up the dimensions, of course, it's going to do better. But then it's going to take a lot more time because that's how neural networks are. But it's still not very satisfying. So we need to sort of change a couple more things. So I need to stay sort of true to my word. And there are some things that I did that I'm not proud about. One of it is that I'm still using an analysis window. I define how big I want my frames to be. That's bad. I'm using hop size, which, again, I define myself. I'm also using a tapering function, the hand window. So now, the next step to say is that why do we want to use frames? Just make explicit convolutions instead. That's effectively what we're doing when we're doing this transformation to a feature space. And what's nice is that it throws away a lot of the sort of phase issues that we had before. There's no need to have similar pairs of bases that you have to sort of mix to create different phases. It actually makes things work a little better. How does that work? So here's the setup again. What we're doing so far is we're taking our frame matrix, multiplying it with our transformation. That's going to give us a bunch of coefficients. If you only look at one column of that setup, it means that we're going to take one frame over time waveform. It gets multiplied by the matrix that holds all of our sort of filters for transformation. And that's going to give us the coefficients coming out, again, a single frame. And if you break this down if you rewrite this thing as a summation, it's basically going to be this formula over here, which almost kind of looks like a convolution, right? So taking that in mind, what we can say is that if we assume that the frames were basically shifted by only one sample at a time, what we effectively compute over here is exactly a convolution between our input and a set of filters, where the filters would be just the rows of the F matrix. So we can take the step that we have up here and just replace it by a convolution step. So now we're effectively blowing up the dimension of our data, but we're keeping the same sampling rate. We're not taking frames. We're still operating in the time domain. We don't have to apply any kind of tapering window, which is nice, because I never know which one's the right one to use. We don't have to specify a frame size necessarily. We specify a filter size. But if you're not comfortable with that, make it big enough and ask for sparsity, and it's going to pick a proper length for it. And we don't have to use a hop size, which again is one of the pain points with all of the NMF stuff. So what does that end up looking like? Well, it ends up looking like this. So we're going to have our sort of front end space, input sequence come in. We convolve that with a whole bunch of filters in our filter bank. Now we're going to have that filter bank as opposed to a linear transformation, well, a matrix transformation. That's going to give us a bunch of coefficients. Again, we're going to do the same rectification and smoothing as we did before. It's going to go through the same NMF type neural net on the top. We're going to do a demodulation. We're going to do a remodulation, get the coefficients. Then we're going to get an inverse filter bank that's going to take these coefficients and take them back to a single time waveform. And it works pretty well as is. So this is what you'd probably like to see if you're into signal processing. This is what you probably would like to see if you're into deep learning. And basically what you have here is a feed-forward network with a couple of skip connections, right? So there's a convolutional layer, which is the front end. Take the activation is going to be the absolute value. There's another convolutional layer that does the smoothing. At this point, I don't even have to specify how the smoothing should be. I might as well learn it, right? It's free. We take the value of that, so we get in a positive space. These steps are basically doing the NMF transformation. And then what comes out gets remodulated by the demodulation we had here. And then finally, there's another convolutional layer to do the synthesis. So it's a fairly straightforward thing. The only thing that's a little different is that we have to have these skip connections to deal with sort of the phase equivalent. Otherwise, it's a fairly vanilla looking kind of setup. And what it allows us to do is to ask a lot of interesting questions for which I don't really have answers. For example, should that layer be an LSTM thing, or is it fine being convolutional? I don't know. Maybe it should be. What about the NMF layers? Well, those could be as well. Do I want to have a soft plus as opposed to ReLUs as my activations? Who knows? There's a bunch of activations you could use, probably getting better results. Do I need to have multiple layers for my NMF? Perhaps. We could try that too. Maybe the demodulation and the remodulation should be another layer. There's no reason why they shouldn't be, right? I just explicitly said, well, I want to divide and then multiply, but maybe I want to do something else. Maybe I want to deal with nonlinear activations. So this could be replaced by a layer, which could itself be convolutional if you wanted. Or maybe my front end should be a nonlinear transformation. Why should it be linear? We don't have to care about those details anymore. So there's sort of a lot of interesting things to play with. And these are not things you would really stumble upon if you were doing it the generic DSP way. The only really question you would ask yourself is, do I want to use a short-term Fourier transform or a wavelet? And that's as far as we can work the analytical math. Here, because we don't have to worry about those details, we can go nuts and see what interesting stuff happens. OK, so we've detected 3 piano notes really poorly. So what, right? It was a good bar trick 15 years ago. Now we're doing more interesting stuff with those methods. So let's see how these ideas could fit in a modern pipeline. So the standard sort of NMF type separation thing you would do is that somebody gives you a mixture of two sounds. So it happens ahead of time that you might know what these sounds are like. And you can have models that are learned beforehand. You want to learn NMF models of those sources. And then you try to use those models to explain how a mixture was composed. And the one distinction that I want to make is that I'm still interested in explaining the mixture. I'm not interested as much in separating a sound, which means that I don't care to get a binary mask. I actually care to sort of analyze the mixing process completely. So here's the process with a couple of equations. First thing we have to do is we have to learn source dictionaries, right? So somebody gives me a bunch of spectrograms that represent different sounds. I throw them into my NMF routine. And then what I really care to keep are the dictionaries that come out of it. Are W matrices that are going to be the spectral templates that describe every sound. Then somebody gives me a mixture. I take the spectrogram of that, or whatever feature transform of that. I stack all of my dictionaries next to each other. So I have this big super dictionary that contains all of the elements. And the only thing I have to do is to find how to activate the elements of those two dictionaries to explain the mixture. If that's done the right way, it means that this dictionary is going to claim everything that belongs to the sound class that it's best at explaining. This dictionary is going to claim all of the other information. So now, if I only wanted to extract one of the sounds, I would take that dictionary, multiply it with the optimal weights for the mixture that I find over here, and that's going to give me just a spectrogram of that sound. Okay, that's a very simple vanilla NMF separation. And what we want to do is mirror the same thing with our deep network. So how does that look like with a deep network? Slightly more complicated, but basically the same process. We're going to have our, we're not going to talk about an adaptive transform at the moment. Let's say that we have one. So we take our transformation, multiply the frames with it, do the smoothing, rectify. There's going to be one layer and an activation that's going to take us to our hidden, to our low-dimensional non-negative representation. And then this is what we care about, how we get from this low-dimensional space back to the original data. Right? So it's a simple autoencoder. So now somebody gives us a mixture. What we have to figure out is what is the proper input in my non-negative space that would produce the mixture that I'm observing. And right now, there's no clear way of getting that for the moment. But if we were to get that, then we'd be able to resynthesize the sources by basically injecting those weights inside our at the middle and only doing a single layer computation to compute the contribution spectrogram of that source. So now the big problem we have to solve is how do we do this? This is something that's very simple to solve doing NMF. With NMF, we're estimating W and H at the same time. In this case, we only have to estimate basically one H. It's a fairly simple process. Here in neural nets, what's going on here? Turns out it's not that bad. So with traditional NMF, what we're going to say is that we know the mixture spectrogram. We already know the dictionaries. We just have to estimate a bunch of weights. That's a simple problem to solve. For the neural network, what we have to solve is we know the output. We know the weights of the network. We just don't happen to know the hidden layer representation in that network. So it sounds like a sort of a funny problem to have. But what's interesting about it is that this is exactly the same thing as solving a regular network. It just happens that the order of your weights and your activations has been swapped, right? So you can still do backpropagation to just estimate what are the right inputs that would produce an output that looks like my mixture. Very simple to do. Again, just a couple of lines of code. So that gives us to the, it takes us to the final kind of form of what we want, which is that data comes in, transformation, smoothing, first layer, low dimensions. You get a bunch of models. And then you essentially have to do this fitting where you already know what the weights in the upper layer are. You already know what the output should be. And you have to figure out the hidden layer representation, which, again, is a simple backprop example. Once you have that, you just propagate that representation through your final layer, and out come the data that you want. And I haven't sort of looked into it into huge detail, but it works pretty much just as well as NMF in at least the few cursory experiments that I've done involving greasy suits in suits in greasy wash water. So what's all this fuss about? So we do get a bunch of advantages, although I admit that most of them are mostly in satisfying my need for not making assumptions. So we don't really have to do much user improvisations when we set up these models, right? We're learning everything. In theory, I shouldn't have to specify anything other than the structure of the network, and then the results should come out. And we're slowly inching towards that. And that makes me very happy, because I think data should do the talking, not established algorithms. The other thing that gets me a little excited is that this fits very well in an ecosystem of easily extendable methods. I could take any layer of what I described and put in any kind of fancy new modification that comes out in say, the next conference, recurrent models, convolutive models, anything of that sort. And then I'm going to get a new architecture that could potentially have a power to do more interesting things. Disadvantages is that we're not really sure that we're going to find optimal transformations. In some sense, the DFT and the DCT are already optimal for sounds. And what we're doing now is trying to find representations, transformations which are optimal for representing sounds, not necessarily for separating sounds. So we're not really addressing the discriminant aspect of this. Although it's easy to split the network and then train into that, but I'm not going to talk about that. The other problem is that it requires a lot of number crunching. So if you're talking about small examples like my puny 3-note piano example, it's overkill to have a deep network like that. It's going to take a lot more time. It's going to be, the results are not going to be as strong. But if you have a much, much bigger data, then your feed-forward process ends up being a lot faster. It ends up being a little bit more efficient on that front. You never want to do NMF with humongous data anyway. And then the data will really give you a lot of the structure that you want. But the other thing that I think is a little bit more enticing going this way is that we can actually get closer to a lot of interesting hardware implementations. So all of the stuff that I talked about, whether it's NMF or whether it's the neural network stuff, requires a ton of floating point multiply and accumulates. And as you all know, our computers are not getting that much faster. They just get more cores nowadays, or maybe we get a GPU and we get some breathing space. But a lot of us here are product people. We've all spoken to the cell phone division, and they said, "Are you nuts? This thing is going to catch fire if you implement these things on it." So, so one of the things that we're working on, and it's really exciting, sort of reinterpreting everything this way, is the idea of using neural nets which are working on just bits. And there was a poster on that Minje was presenting a couple of hours ago, so if you missed it, tough luck. But let me give you the gist of it. With a real valued network, you would basically take a dot product between two vectors, and then it's going to go through some kind of a sort of saturating nonlinearity. It doesn't have to be that, but for now, let's say it's that. What we can do instead is replace every weight and input that's coming in with just a bit value, which could be either, say, -1 or +1. The equivalent of doing a multiplication would be something equivalent to taking the XNOR. And then the equivalent of having a saturating sigmoid is basically seeing if the majority of those bits were on at the end of this different dot product, or if the minority of them are on. And that's going to be your +1, -1 label. And if you look at it carefully enough, it actually turns out that it's going to do roughly the same thing, but it does a very heavy quantization of what's happening. Now, the reason why that's exciting is that if you try to implement this thing in hardware, or at least see what it takes in terms of hardware, we're getting something like 2 orders of magnitude improvement in power and in complexity of the circuit, which means that this is something you could actually fit inside a cell phone as opposed to a humongous NMF filter bank and things of that sort. So hopefully, eventually, this whole pipeline that I've shown is going to be this very deep network. It's only going to be operating on binary values, and then we don't have to worry too much about dealing with the computational complexities. Okay. So the initial goal was explaining mixtures from a waveform. Didn't want to use spectrograms. I didn't want to use my spectrogram additivity assumptions. I'd wanted to throw a lot of those things out. I really, really hate phase. So what I tried to sort of the journey I took you in with for this talk was basically finding ways of going past these representations and coming things which are tailored for just the problems we're trying to solve. There's a lot of interesting sort of ways to move from here, but just wanted to give you a brief idea of how I envision sort of NMF and neural nets kind of playing well with each other. Is this the way to move of the future? I have no idea. As far as results go, it's really on par with NMF methods, so you don't really get an advantage other than the fact that you don't have to specify everything yourself. So if you're not good at guessing, it's probably better, but if you are, then it's probably not. What I find to be most exciting is that it's something, an approach that's trivial to extend to different kind of models. There's a lot of interesting substitutions to make in there, which are things that are very difficult to do in a signal processing framework, but they become trivial when it comes to machine learning. And that's all I had to say. So thanks very much for having me. And
thanks. Thank you. Questions and comments? Brian?
Not him again.
First of all, I thought that was a really great step-by-step walkthrough of the thinking process, so thanks. One thing I wondered, though, for me, one of the weaknesses of NMF was not whether I had to worry about phase or ignoring phase or window size. It's that I generally find I have to seed the matrices with good values to begin with, or I have to give it a training example like this very clear one you gave, which I think goes back to this paper you had from a while ago, where, you know, for example, in this very clear example, you played one of the notes, then another one of the notes, then another one. And that's like the sort of ideal case. You have a piano, so the basis functions are nice and simple, and you showed things to it in beautiful order so that it could learn. And I'm wondering, do you think from the experiments you've been doing that this sort of new framework will help us with not having to seed our training examples quite so obviously, or start our, in this case, W and H matrices with values that are already pretty close to where we want to get to? What do you think about that?
So again, one of the advantages of reformulating everything as a neural net is that you can say, well, you know, I've read this paper that said if you use dropout or if you initialize things that way, it's better. So it definitely gives you more options, right? There's no literature on how to initialize, you know, NMF algorithms, and you know, if the data doesn't have the structure apparent, then they're not going to find it. There are lots of easier ways to regularize neural nets to basically push them towards the direction that you want. So one hope is that yes, you could probably use a lot of those tools to help you steer the convergence towards something that you care about. If that pans out, I don't know.
Okay.
Dan?
Yeah, thank you. So one thing about NMF that you threw away, I think, without mentioning it, was that you didn't constrain the W matrices to be non-negative. So one of the big things that takes away is this sort of additive property of the NMF.
Mm-hmm.
And did you throw that away on purpose?
Yes, because I want to be able to get complete silence, which you would never get. Well, you would almost never get if the constraint was that your weights have to be non-negative. I want to be able to have weights in my layers that say this thing really doesn't have to be there, and you get a big weight that basically obliterates everything else. This is not something that's feasible with NMF. That's why you always get a little bit of a chatter signal whenever you shouldn't have anything. But I could reformulate the more. I mean, you could run the same experiments again with a non-negativity constraint, and it's roughly going to be the same results.
Yeah. So this compositionality has often been a selling point for NMF, but you think that was a mirage or what?
No. Well, it's still there because my low-dimensional representation is non-negative, and I still have to compose my data using that. There's still no cross-cancellation happening, and that's ensured by the activations.
I have a question, actually. I'm still trying to wrap my mind around the whole of the talk, because there's a lot of things, but I'm not sure I understood. And to me, most of it was unsupervised, right? Most of the 3/4 of it were unsupervised. So one question about that is, how do you know that there's any meaning in the H layer first? I think to me, you were kind of lucky that you were able to separate these nodes thanks to that. That's one thing. The second one, I guess in the second part, you started to be doing supervised things, and you proposed that way of forcing the supervision into so I guess it's not really a question. I'm like, is it the do you envision other ways to include supervision in this? How much do you think your H matrix would be interpretable? Yeah, I have all sorts of questions in that regard.
Yeah, you know, whether you want your H matrix to be interpretable is it's kind of an interesting question, right? If you're trying to do you know, music transcription, yes, that's the only thing that matters. If you're trying to do source separation, I couldn't care less what it looks like, as long as the proper subspaces do their job and pick out what they should claim. You know, if you want to do music transcription, then you probably want to add some kind of a regularizer that imposes the constraints that you want. If it's only monophonic music, you just say, well, I want my H to be super sparse, and then it's going to be interpretable. Obviously, if you're trying to explain, you know, 3-dimensional data like that using 20 dimensions, you're not going to get an H that makes sense. But if you put the right sparsity in the right places, it's going to start looking like what you want. So, you know, everything is optimal given the right criteria.
So the follow-up question, I guess, before I understood that we were doing unsupervised, because it took me a while to understand like we were actually unsupervised up until the middle, and I was like, why doesn't he why does he use an autoencoder? Of course, because you are unsupervised. But what about training that same not autoencoder, but similarly, but only instead of using x tilde or x as the output, just use one of the sources and train that same pipeline?
Yeah.
Would that work? Was it like better than the supervised version?
So the things that I've shown here are basically on par with NMF in 2007 or so in their sophistication. Sure, you could have an autoencoder that basically splits into two. So mixture comes in, two separated sources come out. You get the optimal transformation for the separation, not for representation. And you know, all of those things work out. It's definitely doable. It's not something that I care that much about. I think of separation as being a subset of the real question, and the real question is, how is my sound composed, or what is my sound composed of? So I'd like to keep things as unsupervised as possible, because I want to be able to see activity that I can interpret, not so much extract what I wanted. If I really wanted to extract stuff, I should be using binary masks. I should be doing a lot of different things.
Well, I guess there's tons of methods that have been discussed today that should be combined with your approach.
But definitely, a lot of the extensions that were talked about today, and a lot of them, by the way, had a lot of overlap with those ideas. You know, they could fit in very well in that framework.
Thanks.
Yes, I really like this talk. The one thing about the classical methods is that the analysis knows something about the synthesis because they're the inverse of each other. Whereas when you put that into the neural network analysis, I mean, I don't know if I understood that correctly, but did I understand correctly that analysis and synthesis don't know anything about each other? And if so, is there a need to work on the training algorithms to enforce the kind of structure you need for this to work?
You are correct. The only constraint that we have is that the input that goes through this process should come out the same on the other end. I could very well say that I want to have my analysis transformation to be equal to the transpose of the synthesis. So that would make an orthogonal transformation. Do I care to have orthogonality? Not really. You know, I'm not doing analysis. I don't care about the math properties of what I have here. So it doesn't buy me anything. So I'm sort of, it's a little bit of a waste because, of course, what I'm doing here is that I have more parameters than I need to, perhaps, right? Because I have to estimate an analysis and synthesis filter bank. You know, maybe those things should be related somehow. But it's not something that I guess I didn't bother to examine it too deep.
Maybe that's a clue for neural network people to maybe think throwback propagation, you know, throw one more thing, which is maybe a received ID. I don't know. Anyway.
Yeah.
Thank you.
So this is more of a question to trying to understand the model better. So you said that you don't care about phase anymore, but are you really throwing away the phase? So it seems like the way you resynthesize it, you're still somehow implicitly using the noisy phase. And all of the problems that we have with noisy phase when things are extremely noisy is going to happen here again.
I think the keyword here is modulation. So there's no guarantee that what you're going to get inside the W matrix is going to be sinusoidal, in which case phase is not really, you know, phase. So the only thing I'm saying is that I'm just normalizing my coefficients or undoing their sort of a short-term envelope and then imposing a new envelope after that. On a sample-by-sample basis, that's equivalent to doing phase if your coefficients in the transformation are actually sinusoids. But what's the point of talking about the phase of something that's a sort of a mini waveform like those bases I was finding?
Don't they still have a phase? There may not be a sinusoid, but it still has a phase, right? Or I mean, I guess the question is more along the lines of if things are noisy, you're still going to have the same problems that we have with noisy phases if you're taking complex FFT, for example, because whatever comes out in your analysis phase is going to look more more like the noisy signal than the individual components that you're trying to reconstruct in the end, right?
Depends on what the front end transform ends up looking like. And I'm not going to have any intuition here because it's very easy to talk about phase and phase cancellations and all that stuff when you have a nice Fourier transform in the beginning. In this case, I can't quite visualize it in the same framework. The only thing I can say is that I'm demodulating my coefficients, and then I remodulate them with something else. And in the case of complex numbers, that's the same thing as taking out the phase and then putting it back in later. Now I'm taking out something else and putting it back later, but it's not clear what that is.
I guess you could train that process to be robust to noise, for example. Like change the transformation such that when you train on a lot of data and that phase, but thing that you're taking away, the modulation you're taking away, actually it doesn't get corrupted that much by noise.
Yeah, okay. and if you have the right skip connections, then it doesn't even mean that phase will matter because your transformation might have features which wouldn't really have the problems you're finding with the short-term Fourier transform.
Very nice presentation, thank you. One question, you had one slide where was the comparison with NMF activations and neural network activations, where the NMF, the deterministic, it had something, in the neural network it was totally zero. Yes, exactly, and it has this, I would like to ask, what was the algorithm you used for the deterministic NMF? The upper figure.
Just a regular KL type NMF.
Because I'm curious if this would happen with an alternatingly squares algorithm, where we can have exact zero, where in KL and Itakura Saito they have this problem, they cannot give exact zero for the factors, because they are multiplicative.
Yeah. I've never got results that I was proud of using alternative minimization.
Okay.
So I'm pretty sure it wouldn't.
Thank you.
Yeah, I have a small comment. I think it's better to use multiple hidden layers in the neural network to compute the low-rank activations to simulate the process of computing the activations of NMF.
Yeah, I mean, it's unexplored territory. So, yeah.
In my opinion, it's hard to get it with only one layer.
Yeah, fair enough.
Yeah. Eric?
Okay, I think I have a question, but I need a clarifying question first. The objective function that you're optimizing to, it's reconstruction error with sparsity?
No. Well, ish. Let me see what's the because there's a bunch of networks. So this is the full thing. So it's mean squared error on the essentially time data, and sparsity on the coefficients and on the low rank space.
Okay, on the two hidden representations.
Yeah. Now, if you go a few slides back, then you get these guys, or actually this guy. And here the cost function is the sort of KL-like divergence between my non-negative input and the non-negative output.
Okay. Okay. So one of the problems that I've run into, and I'm curious if you've seen this so far, autoencoders on time domain audio data, they're really great for like low frequency components, but you really get burned on high frequency and stuff because the scale factors are all wrong. Do you have any insight or perspective on how to kind of like flatten the different, in the same way that wavelets would kind of adjust for the scale factors at the different bands?
You can use a preemphasis to put more energy in the high frequencies, so then they're going to start mattering more. That's one thing.
So would you learn that?
I would love to. The only problem with learning it is that the cost function is basically our hearing system. So if you could plug somewhere in your ear and get a feedback, then yes, I would learn that.
So we're back to peak then, in terms of trying to learn that. I mean, that's really what it boils down to, right? Like,
Yeah.
any kind of Euclidean distance in time-domain space is going to pull it to the averages.
Again, it depends on what you're trying to get, right? If you want to do separation that sounds good, then you have to put in some knowledge about what our ears like, right? If there's a ground truth that's waiting to be discovered, like in the case of the piano data, then what our ear says is kind of irrelevant.
Yeah.
It's in there in the data. So it really depends on the application.
Okay, awesome. Thank you.
Thanks.
All right, let's. If there are other questions, we should take them to the next session. So let's thank Paris again. Okay, so that concludes the day. So we had many interesting talks and posters. I'd like to thank you all for coming, and the speakers and poster presenters. I would like to remind you that we, some of us, I hope many of us, will be going to a social session at flight 151, I think. And before we stop, and after thanking you, I would like to thank Hank Liao, who was my co-organizer for the day and who did all the tough job of actually organizing the thing. So Hank, can you stand up? Thanks a lot. And we hope to see you next year. We don't know where yet. In 2 years, probably in New York. And thanks again.